Okay, yeah, good day, everyone. It's an honor to present the preliminary studies in optimizing deep learning for computer vision. We are working on memory traffic reduction across convolution neural network layers, and this is a joint work between me and my student and Professor Xu at National Taiwan University. Here is the outline of the talk. We first compare human vision against computer vision, how human sees is different from how computer sees. Then we'll analyze the underlying technology for human vision and computer vision. And then we'll briefly talk about deep learning and the convolution neural network. And finally, we'll motivate our work on memory traffic reduction and the related work on what's our method and the experimental results. Finally, we conclude. Let's start with vision. If you can see this lady, that means you are employing human vision, not computer vision. Computer vision is to teach computer to see. What computer initially observe is this 0 or 1, but not the lady. And if we look at the definition of computer vision, it's an interdisciplinary scientific field that deal with computers, how computers can be made to gain high-level understanding. So if the input is image or video, the output can be another image or fundamentally language that describe what this image is about. So computer vision include processing and analyzing and understanding of digital images. In this definition, image processing is part of computer vision. And computer vision is an important field. As you can see, in year 2021, the current revenue is about $40 billion, and it has many applications, including agriculture, automotive, sports, entertainment, and so on. How humans see is different from how computers see. If you look at the human brain, the parietal lobe and the occipital lobe are responsible for computer vision, for human vision. But how computer sees is different. When you see an image, basically it's divided into these tiny squares called pixels. And we can see that if an image of 1024 by 1024, you have about 1 million pixels. And each pixel has RGB, we call it channels, red, green, blue channels. And how computers see these days is typically using neural network. You can see all these perceptrons connected with edges, and each edge is associated with weight. And if you have many hidden layers, it's called deep learning. And as you can see in this picture, artificial intelligence was proposed roughly around 1950. And the machine learning is a subfield of artificial intelligence. Deep learning is an even smaller field, and they are from different eras. And typically, deep learning is popular in the past 8 or 9 years also. And deep learning neural network, let's recap. If you have more than a hidden layer, it's called deep learning, and you have an input and output. What's CNN example of deep learning? You can see from this figure, this convolutional neural network consists of at least 4 layers. The input is an image. In this example, it's a bird image. And you can see we first start with the convolution layer. I'll describe the details of convolution layer later on. But you can see this is the first stage, the convolution layer. That's for feature extraction. And the next stage is called max pooling stage. Max pooling is for dimension reduction. So if you have this convolution operation of this 3 by 3 matrix each time, let's call it a convolution matrix of 3 by 3. And later on, the max pooling stage can reduce the dimension of 3 by 3 into 1 by 1 or 2 by 2. And the next stage is called fully connected layers. After the dimension reduction, you can use fully connected layers for classification. The output of classifier is the following. Is it a bird? Is it a sunset picture or a dog picture or a cat picture? If this is a bird image, ideally, the probability of this bird classifier output should be almost 1, and the rest should be almost 0. And here we need to mention the last layer, it's called softmax layer, because the output of fully connected layers for all these multiple outputs, they may not add up to 1. So you have to use softmax layer to normalize them, and so that they all add up to 1. So for example, if the probability of this picture being a bird is 0.99, the other classifier outputs should be all add up to 0.01 only. So as we can show you in the coming slides, we use a sliding window in our convolution layer. Basically, you slides this window of 3 by 3 convolution matrix across this image, and each window is performing a convolve operation, and so it's basically an element-wise inner product. Let me show you in this picture. If this convolution matrix is 3 by 3, and we slide the window across this input image, and you can see why the resulting value will be 4, because when you do element-wise multiplication and accumulation, there are 4 overlapping ones, because the top left and the bottom left and the bottom right, they are all ones in both input image and also the convolution matrix. And if you see the one here in the middle, then here is also 1. So exactly you have 4 overlapping ones out of these 9 elements. And so as a result, when you add up all these element-wise multiplication results, the answer will be 4. And similarly, if you look at this bigger picture, on the top left corner of the image, they are all zeros. And so when you convolve this with this convolution matrix, we sometimes call this weight matrix. So in this case, each element in this weight matrix or convolution matrix is 1/9. Okay, so you have 9 elements here. And of course, if you do a convolution with input image and this weight matrix, the answer will be 0 because they are all zeros. So that's exactly what you got here. And the next one is 10 because you have only one non-zero location after the multiplication of 90 and 1/9, the answer is 10. And if you keep sliding this window, the next will be 20 because you have 2 non-zero elements, and then will be 30. Okay, there's another 30 here after you do more convolution. Here, what's the answer for this convolution over this place? Remember, this is our convolution equation. Basically, you are doing inner product of this particular matrix G and the filter called F. And here, because you have 5 non-zero elements here, and the convolution matrix, each element of that matrix is 1/9. So apparently, the answer here should be 50. Okay, let's move on to the motivation for memory traffic reduction. Because of Moore's law, the ARU, arithmetic larger units, is not as expensive as this memory traffic. Typically, we have a large number of parameters. The weight matrix can be huge. Such parameters are too many to fit in the limited on-chip SRAM. Therefore, we need to make careful management to the most effective use of the limited on-chip SRAM. There's a bunch of related work on memory traffic reduction. In 1991, Monica Lam, who is my advisor at Stanford, she and her student at the time, Michael Wolf, wrote a seminar paper called Data Locality Optimizing Algorithms. In 1999, my advisor and myself, we wrote Swift Explorer. Swift stands for Stanford University Intermediate Format. That's the compiler from Stanford University. We, in addition to the unimodule transform, which is interchange, reversal, and the skewing, and also we have this tiring from this 1991 paper. We added reduction and array contraction to the toolbox, so we can do more memory traffic reduction. And many reduces CNN memory traffic via data compression. There are 2 important approaches to data compression. One is from the Iris paper from MIT, they propose quantization. So instead of using many bits to represent a weight value, you can just quantize it and use fewer number of bits. Another approach to data compression is weight pruning. Bill Daly from Stanford and his students proposed this weight pruning in NIPS conference in 2015. And also they improve upon their weight pruning approach in the ICLR conference the following year. ICLR stands for International Conference on Learning Representation. Intel also proposed their version of weight pruning called dynamic network surgery. And that's from NIPS 2016. Here we focus on scope of 1 CNN layer versus 2 CNN layers. In our example, we use ResNet. For example, ResNet 34 usually has 2 adjacent layers with the same channel size or same number of filters. It's called M in our notation. So doing 2 adjacent layers makes sense because, like I said, you have 2 adjacent layers with the same number of channels usually. So, for example, in this 7x7 by 512 case in the ResNet, the number of channels is 512, right? And the input image or the inputs OX, that's so-called OX and OY, they are 7x7. So we focus on scope of one just intra-layer, 1 CNN layer, or inter-layer. That's in our case between 2 adjacent layers. We have proposed an algorithm to schedule 2 adjacent layers of a CNN, and our goal is to reduce traffic between DRAM and the local memory more than allocating to buffer to only 1 single layer. And so typically a lot of people just focus on allocating the buffer to only a single layer. But in our case, the feature map can be reused for the next layer. So let's first start with a quick survey on other multi-layer work. The general case is the 1-layer case. It's proposed by Luca Benini and his students in 2019. They proposed an analytical memory bandwidth model for RUBNest optimization targeting architecture. That's where an application can manage the buffers. They tire the RUBNest, but they only limit themselves into 1 single layer. Arizona State University proposed DMACE runner in ICASP in 2020, and they use this model to spatial temporally execute a perfect nested loop on data flow accelerators. At Stony Brook University 5 years ago, Professor Elwani proposed this fused layer CMA accelerator. They designed their own hardware, and they can choose which layers to fuse, and then tell the hardware how much on-chip storage to add to use their schedule. Okay, so let's talk about our methods next. We assume a 2-layer memory hierarchy. The on-chip SRAM is much faster, but if you need to go off the chip to the DRAM, it's more expensive. This is natural consequence of Moore's law. The off-chip communication is not following the Moore's law per se, and as a result, the RU and the on-chip access is much faster than off-chip access. Okay, let's talk about the convolution. Here is the recap. You have a number of channels here, and you have M filters. In our example earlier on, you have 512 filters producing 512 channels. And in our case, Fx and Fy, they are 3 by 3. They are our weight matrix. So the convolution matrix is 3 by 3, and the output is 7 by 7 in our 7 by 7 by 512 example. Here's the convolution loop next. You have a 6-layer loop next, and you have a number of filters and a number of channels in the outermost loops. And here you have a 7 by 7 in the innermost groups. You have a 3 by 3, and as you can see here, it's inner products here. And in our example, we can tire the outermost loops. The 4 outermost loops are good for tiring, but the input is 3 by 3, so we don't tire the innermost loops. For single-layer convolution scheduling, Luca Benini proposed a method to find optimal scheduling for single convolution. Okay, the loop after tiring consists of 10 deep loop next, because like I say, the two Fx, Fy, the 3 by 3 loops in the innermost ones don't need to be tired, but the outer 4 loops can be tired. Each tiring results in 2 loops being generated. So together you have 10 loops. The memory traffic can be calculated. For this example, you have the inputs, the weight matrix, and the output, because a single layer you need to read each time. So you have a factor of 2 here. And the data flow schedule selection is as follows. You enumerate different loop orders, tire size, and the buffering levels, and choose the combination that yields the minimum off-chip memory traffic. And for cross layers, we can leave the outputs feature maps in the buffer, and as a result, we can save the reloading from DRAM. And we only consider 2 adjacent convolution layers. The cross-layer memory traffic is also analyzed here, and here is the result of 56 by 56 by 64. So the number of channels is 64, and the OX and OY are 56 in our example. And the buffer size is 512 kilobytes. And so here, in the interest of time, let's go directly to results. You can learn a lot from the results and save your time from reading in the middle. And we use the Gemini simulator from UC Berkeley, and we omit the normalization and the railroad layers because these layers incur very small number of operations compared with convolution layer. Here is the result of our ResNet 34. And this is a single layer scheduling output. As you can see, if you increase the buffer size, of course, the memory traffic to DRAM can be reduced. And here you can see that when the buffer size is big, like 512 kilobytes, then the memory traffic employing cross layer, the memory traffic can be reduced. But if the buffer size is small, like in this case, it's 64 kilobytes, you might as well just use up all your SRAM on a single layer. And here is another results. When you go through ResNet 50, you have many layers because, as you remember, this is deep learning, and the OX and OY value will vary. Not just the feature map size will vary, the number of channels will vary as well. And for ResNet 50, here you can see you can increase the memory traffic utilization by over 10% here. And but if you have later stage like 14 by 14 by 256, cross layer may not help much. So a quick 2 slides on discussions. If all output features can be put into the single buffer, the cross-layer traffic will definitely be lower than the single-layer traffic. In many cases, just giving most of the buffer space to a single-layer tiring work the best. Our comparing algorithm will know when cross-layer transformation will help. And we are exploring other techniques, and including, for example, the weights matrix optimization, because those weights are runtime constants. We can do constant folding, and then the W matrix can be handled as a constant. So many reference to the weight matrix can be eliminated. Recent advancement on ML weight pruning, machine learning weight pruning techniques can overturn the weight array W into a sparse matrix with 90% zeros. So you can reduce memory traffic that way as well. Finally, let's conclude. We have observed that the on-chip SRAM buffer may not be fully utilized by loop tiring transformation. So some leftover SRAM could be used to keep the output feature map from one layer to the next layer. We have shown such cases, and then we've come up with transformation to enable such data reuse to further cut down the off-chip memory traffic. And we have studied the situation. The comparator could consider transformation for cross-layer schedules. Thank you for your time.